Hey everybody, my name is Chris and I'm a tutor here at Chegg.com, and I mostly do math and computer science. So here we want to find the Taylor series centered at x equals 2 for the function f of x equals the natural log of x. So remember that in general the formula is going to be, let's go to page 3 here, the sum from n equals 0 to positive infinity of the nth derivative evaluated at a over n factorial multiplied by x minus a to the n. Okay, this is the Taylor series for f of x centered at x equals a. Okay, so in our case, our f of x is the natural log of x, and our value of a is 2. So what we want is the sum from n equals 0 to positive infinity of the nth derivative evaluated at 2 all over n factorial, and then multiplied by x minus 2 raised to the n. Okay, so what we want to do is repeatedly evaluate the nth derivative at 2 and see if we can come up with a pattern that's going to simplify this coefficient here. And luckily for the natural log function, such a thing does happen. Okay, now so let's start looking at derivatives. So when n equals 0, what does that mean? Well, we're taking the 0th derivative, but when n equals 0, that's really just the function itself. So the 0th derivative is just the natural log of x. Okay, so and then in that case we have the 0th derivative evaluated at 2, which is natural log of 2. So that one's going to be kind of kept separate from everything else. Now let's see what happens when n equals 1. Well, then we have the first derivative, f primed, so I'll just use that prime notation. F primed of x equals 1 over x. Now I'm not going to evaluate just yet. Instead of evaluating now, let's go ahead and continue with the derivatives and see if we can detect any patterns here. So what happens when n is 2? When n is 2, we have f double primed of x equals the derivative of 1 over x, which we know is negative 1 over x squared. What if n is 3? Well, then we get f triple primed of x, which we know, well, that's going to be the derivative of negative 1 over x squared, and we know that that's going to be negative 1 times negative 2, which is actually just 1 times 2, so let's go ahead and write that like that. 1 times 2, all divided by x cubed. And yeah, 1 times 2 just simplifies to 2, but there's a reason I'm writing it like that. So let's continue with a couple more. I'll use a different color here for readability. N equals 4. Then we get the fourth derivative of x. That's going to be the derivative of 1 times 2 over x cubed, which is going to be negative 1 times 2 times 3 over x to the 4th. And then one more here, and we'll start to see a pattern emerge. If n equals 5, then we get f to the 5th, or sorry, the fifth derivative of f at x is going to be 1 times 2 times 3 times 4, and then that's it, all divided by x to the 5th. Okay, and then this, to find this, we just take the derivative of the fourth derivative, and the fourth derivative was this right here. So if we take the derivative of that, then we get this. Now, do we see a pattern emerging here? So notice for the n equals second, third, fourth, fifth derivative, what do we have on top? 1, 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4. So notice we're sort of taking like a factorial thing up here, okay? Where the factorial is starting from n minus 1. So when n is 5, the largest number on top is 4. When n is 4, the largest number on top is 3. When n is 3, the largest number on top is 2. And what else do we have in the top? Well, in the top, we also have positive, negative, positive, negative, positive. And if we were to do the sixth derivative, this pattern would continue. We'd have negative. So we see that we're alternating between 1, negative 1, 1, negative 1, 1, negative 1, and so on and so forth. So that actually tells us that we're probably going to have something like negative 1 to the n, or maybe negative 1 to the n minus 1, something like that. Okay. It's actually going to end up being this one, which we'll see soon. But anyway, and then there's one more thing that we want to point out, which is what happens in the denominator. So for n equals 1, we just have x to the first. For n equals 2, x to the second. N equals 3, x to the third. N equals 4, x to the fourth. N equals 5, x to the fifth. So that's a pretty simple pattern there to detect. So what do we have in general? In general, the nth derivative of f evaluated at x is going to be what? Well, when n is 1, in other words, when n is odd, we don't have a negative, we have a positive. When n is even, we have a negative. N is odd, we have a positive. N is even, we have a negative. Okay, so remember up here we wrote negative 1 to the n or negative 1 to the n minus 1. So which one of these will it be? If you have alternating positive negative like that, you're always going to have one of these two. And if you want to know which one it is, you look and say, okay, when do I have positive, when do I have negative? Well, for this particular example, we have positive when n is odd and negative when n is even. So which of these two over here gives us that? Well, if we have negative 1 to the n, so let's take, for example, negative 1 to the n equals 2. That's going to be positive 1, so when n is even, we have positive. That's actually not what we have here, because when n is 2, we have negative. Okay? So that tells us then that this is the one that we're going to use. Because when n is 2, we have negative 1 to the 2 minus 1, which is negative 1 to the first power, which is negative 1. So with this one, when we have an even n, we have a negative, which is what we were looking for. Oops. Okay, so let's get rid of all that clutter up there. So that tells us then that we have negative 1 to the n minus 1 so far. And remember, we said we have n minus 1 factorial. Okay? Because here when n is 5, we have 4 times 3 times 2 times 1. When n is 4, we have 3 times 2 times 1. When n is 3, we had 2 times 1, which is 2 factorial, and this was 3 factorial, 4 factorial, and so on. And that pattern is going to continue. Okay, if we were to take the sixth derivative, we would end up with negative 1 times 2 times 3 times 4 times 5 on top. So that's why we have the n minus 1 factorial up there. And then on the bottom, remember that was the easier pattern. When n is 1, just x. When n is 2, x squared. N is 3, x cubed, and so on and so forth. So for general, the nth derivative, we're going to have x to the n on the bottom. Okay? So let's go ahead and move on to page 2 now. So let's go ahead and rewrite this a little bigger so it's easier to see. The nth derivative of f evaluated at x is, in general, negative 1 to the n minus 1 times n minus 1 factorial, all divided by x to the n. Okay, so in particular then, remember what we really care about is all the stuff evaluated at 2. Okay, this is really what we want, all that stuff evaluated at 2, and then divided by n factorial. So let's not forget that. Okay. So the sum from n equals 1, I want to start this at 1. Why at 1? Well, in general, the Taylor series, power series, they start at n equals 0. But n equals 0, remember, we were treating this separately. Okay, we're treating that one separately, and then we're starting with the series at n equals 1. So that's why we're doing that. So n equals 1 to infinity of the nth derivative evaluated at 2 divided by n factorial times x minus 2 to the n is going to be n equals 1 to plus infinity, the sum of that, of negative 1 to the n minus 1 times n minus 1 factorial all over 2 to the n. Okay, because if this is the nth derivative evaluated at x, then if we plug in 2 for x, that's just going to be 2 and then 2. So that's why we have a 2 to the n right here. Okay? And we're still dividing everything by n factorial. So dividing, let's maybe make that easier to see. Dividing by n factorial. And then we still just have x minus 2 to the n. Okay? So dividing everything by n factorial there. And let's go ahead and simplify a little more. And we're going to get the sum from n equals 1 to plus infinity of negative 1 to the n minus 1 times n minus 1 factorial all over 2 to the n times n factorial. Okay, so if we have this whole thing up here and we're dividing all that by n factorial, then that's just the same thing as saying this right here. So we can just move the n factorial into the denominator with the 2 to the n right here. Okay, and then we still have times x minus 2 all raised to the n. Now, there's another thing we can do to simplify, which is going to be kind of nice. So notice up here we have n minus 1 factorial, and here we have n factorial. And remember that n factorial is just n times n minus 1 factorial. So let's go ahead and rewrite this n factorial as n, oops, keep the same color, n times n minus 1 factorial. Now that's really great because then these cancel. So the n minus 1 factorial here cancels with this one here. And then what we're left with is the sum from n equals 1 to plus infinity of negative 1 to the n minus 1 over 2 to the n times n, and then we still have x minus 2 to the n. Okay, that's to the n up here. Now that's not quite everything because remember we still have this piece right here, so we can't forget that. So let's go ahead and go to page 4, because page 3 we already had something. So then what we have is natural log of 2 plus the sum from n equals 1 to plus infinity of negative 1 to the n minus 1 over 2 to the n times n, x minus 2 raised to the n. This is the Taylor series for natural log of x centered at x equals 2. Okay. Now if you're wondering why do we just slap on this natural log of 2 and just add it to that, well, because remember in general what we have is this, the sum from n equals 0 to all that, but when n is 0, what's this piece right here? That's x minus 2 to the 0, which is just 1. Okay, so x minus 2 to the 0 is just 1. So when n is 0, we just have this piece right here, the 0th derivative of evaluated at 2, which is natural log of 2, and we're dividing it by 0 factorial. Okay, we're dividing it by 0 factorial, and 0 factorial is just 1. So when n is 0, the corresponding term is just the natural log of 2. And because the Taylor series has to start with n equals 0, we have to make sure that we include that in our final answer. Okay, so that's why on page 2 I said we're not done here. Okay, so we have to be careful with the n equals 0 term. So this is our final answer here. Natural log of 2 plus the sum from n equals 1 to infinity of negative 1 to the n minus 1, or n plus 1 if you prefer, divided by 2 to the n times n, all multiplied by x minus 2 to the n. That's the Taylor series for natural log of x centered at x equals 2. So I hope you found this video helpful, and thank you for watching.